So I'm almost discussing the content he shared with me. So yeah, I modified few bits, but a significant amount of information is whatever Professor Case Reddy shared with me. I'm discussing. So probably the outline or the content of these 3 days will be the same as what we that has been discussed in batch 1 and batch 2. Okay. So and also 1 or 2 points before I start. So let it be two-way, so that whenever you have anything, you do not have to wait towards until the end of the presentation. You always can interrupt me whenever you want. If you have any clarification required, I'll try to answer as much as I know. It is not that I know everything, but I'll try to answer as much as I know. And if I do not know, obviously I can come back with you the answer as well. Obviously, maybe some of the aspects, maybe implementation aspects, you know better than me. I can learn from you as well. So with that, let me start what I wanted to discuss today. So first, so all 3 days,
Dr. Kranti, your voice is not audible.
so I think someone has muted me for some reason. Okay. Is it audible now?
Yes, perfect, sir.
Okay.
Okay now.
So what we'll be discussing for all 3 days, it is the same content, but we are repeating one. And so in the first, today, I'll try to discuss what are the principles of payment design. So I'm assuming, or I hope that by the end of today's presentation, one should be able to understand the principles of any flexible payment design guidelines. It doesn't matter IRC 37 or maybe if we are talking about some say Australian guidelines or European, some French guidelines or UK guidelines. Okay, we should be able to in a position to understand what are the principles involved in. I'm not deliberately saying US guidelines, because US guidelines, recent guidelines, like we call it as mechanistic empirical payment design guidelines, they are much more comprehensive. Maybe we might not be covering, we will definitely be covering some of the aspects, basic fundamental aspects, but it is much more complex than that. For us to understand MEPDG, mechanistic empirical payment design guide, which is the latest guidelines, although not all states in US are implementing those guidelines, but most design guidelines you should be able to understand why each specification is there, why each requirement is there. So that is the objective of today's presentation. Obviously, that means we should be able to understand why each requirement within IRC 37 exists. So tomorrow I'll be repeating the same what we discussed today, but with the intention of understanding IRC 37 exclusively. So we'll be discussing different clauses and different aspects in IRC 37. So how we can design a payment using IRC 37 with maybe an introductory examples. We will discuss that tomorrow. So the third day, what we'll do is maybe we take in practical examples, maybe a couple of examples with different kinds of scenarios, and so that we'll have an hands-on experience on using the tools that we use for IRC 37 flexible payment design. Right. So obviously today, although I said principles of payment design, it is we are mostly focusing on principles of flexible payment design. Okay, although some of the aspects we are discussing are applicable for the concrete payment design. So yeah, to introduce myself, although my introduction has been done. So I'm Kranti Kuna. So I'm assistant professor at IIT Kharakpur. I've been here from 2017. So today I'll be giving 2 lectures, although I could have fit everything in one lecture. but I deliberately made into two lectures. First one, I'll be discussing primarily the overall principles of payment design. And the second lecture, what I'm going to discuss is more focusing on the traffic loads. Okay, so particularly calculation of vehicle damage factor and also other aspects of traffic related aspect, traffic load related aspects. I'll discuss separately in a separate lecture. Although some of the aspects I still discuss in this presentation, but the majority content of the traffic related or traffic load related aspects I'll be discussing in the second lecture. So first I'll start with introduction to what are the different pavement types, and just to give some background of what we are going to discuss, and then we'll discuss different types of payment. But the majority of the lecture will be on the flexible payment. Okay, but why we call flexible payment as a flexible payment, that I'll discuss. And then different performance aspects we'll be discussing. Then what are different design approaches. Okay, so what is the typical design approach in IRC 3070? As I said, like for example, although I'm saying flexible payment, it is applicable for concrete payment design and also some of the principles, and also flexible payment primarily we will be focusing on the highway payment design. But what are the approaches that we have in say port payment or airport payment, like a runway, that also we'll be discussing. And what are various design factors we consider for design of a flexible payment, and what is the design framework. So I'll conclude this lecture with a design framework. So basically in the design framework, I'll try to summarize whatever we have discussed in this entire lecture, and how we put that in when we are designing a flexible payment. So that is entire objective of this presentation. So maybe first few slides may be very introductory. Most of you might know these aspects, so I might go a bit quickly, but I hope it is not too boring for you. So coming to the definition of payments. So payments are structures designed, built and maintained or a foundation. Okay. So one of the primary objective of a pavement.
Excuse me.
Yes, please.
You are going to share the slides or how?
Oh, sorry. Yes. I'm going to. I thought I'm sharing slides. Apologies.
Okay. And can we get the copy of the slides also?
Yes. I'll. Can you see my screen now?
Yes.
Okay.
Yes,
I thought I'm
yes, sir, yes,
discussing.
sir.
Sorry.
Yes, sir. Seen as of the slides.
This is the first thing I should be doing, but hopefully this is now visible.
Yes, visible.
Okay. So this is the content outline of my presentation, which I was discussing now, like introduction, payment types, what is meant by performance, and what are various design approaches, like a mechanistic, what is empirical design approach, what is mechanistic empirical design approach, what are the various design factors. So we have primarily three design factors. One is related to traffic, which is the important, and then material related factors, and the third one is climatic condition. Okay, so we'll be discussing briefly at high level about these three design factors. Okay, what are how material factors influence the payment design, how climatic factors influence the payment design, how traffic factors influence the payment design. But as I said, I'll have a separate lecture which will discuss this lecture to primarily be focusing on the traffic related aspects of the payment design. And finally, as I was saying, we'll conclude this presentation with design framework. So as I was saying, one of the primary objective of any pavement is to protect the foundation. So here foundation is you can say if you are having if you are constructing in a cut area. I hope you know what is cut and fill, but if you are not familiar, maybe let me say if this is your existing topography. So for example, obviously for geometric purposes, you will have some profile. Okay, so I assume this is your geometric design profile you developed, design based on geometry. Then this is this area. So this is existing topography. You will cut this, and what you do is you make use of this material and fill here. Okay, so this is cut. So this is cut and this is fill. So depending on where you are constructing, so if you are consider say if you are filling the fill area, so you will have an embankment here. So on the top of the embankment, you will have a subgrade. So essentially, the objective of a pavement is to reduce the amount of stresses that are going onto a naturally existing foundation. So that is the main objective of a pavement. Okay, so essentially what we have to try to do is we put sufficient amount of thickness, obviously with the different pavement layers, so that the stresses upon the existing material is within the permissible limits. What are those permissible limits and etc. we'll be discussing later. Okay, so that is foundation. So foundation is subgrade layer prepared using suitable soil. Okay, suitability, whether it is a suitable or not, that is a different topic. But the MORTH guidelines, MORTH, the guidelines, and also some IRC guidelines, the relevant IRC guidelines will suggest what is the suitable soil. And other materials recommended by the obviously MORTH document. If you, I think you are all of you are aware of MORTH document. Compacted using OMC to density of at least 97%. Again, this 97% is given in the MORTH document and relevant IRC documents as well. Of a maximum dry density. This is if you carry out the Proctor test, modified Proctor test. Obviously, you might be knowing what is optimum moisture content and maximum dry density. So if we are compacting the soil to 97% of it Proctor density, then we compact. Basically, that is what the subgrade is. So in essence, maybe. So according to the definition of MORTH, subgrade layer is prepared to a compacted, say top 500 mm. We consider it as a subgrade, okay, for highways. And below which the embankment, we have to compact it to the 95%. And for low volume roads, it is 300 mm thick. Okay, this is the reason why I'm discussing, although these might be discussed in later lectures. Obviously, you will have a pavement construction and those aspects. These might be discussed in that. But what I'm trying to say here is we have to protect those two, the subgrade layer, which is the foundation of a pavement. Okay. So that is the basic objective of a pavement. So where do we have pavements? Obviously, we'll have airports. We have a pavements, haul roads, loading yards, and low volume roads. And as you can see here, we have a highway, and this is port as well, port pavements. At all these locations, we'll have pavements. Obviously, the approach and the and also design, we can say design of airport pavement is different from a design of a highway pavement, because the type of loading is different, the number of repetitions are different. Okay, there are many other factors as well. How the load is applied is different. Vehicular velocities are different. So there are many other aspects that need to be considered. For example, highway, the load repetitions might be more, whereas for an airport, the load repetitions might be less. But for example, port pavement, the load intensities are very high. We are talking about like say 1500, 2000 kilopascal stresses. Whereas for the road pavement, we are talking about 750, 800 kilopascal, maybe sometimes 900 kilopascal stress levels. So depending on the all these aspects, the design approach is different, and also design will be different. So, but obviously we'll be more focusing on the design of highway pavements. So as I was saying earlier, we have typically three different factors. Okay, one is traffic, one is climatic, and the third one is material. So regarding the material, the subgrade, the material characteristics, the material of the subgrade is the most important one, because we have less control over the what type of subgrade we can choose. We can choose other materials, whether we want what type of asphalt material, what type of granular material, whether you want to stabilize those, you want to use cement treated base, all those options are available. But with regards to the subgrade, we have less control over it. That's why most of the designs, they have one of the important design input is the subgrade characteristics. The strength of only the subgrade and effective strength of the subgrade, the layers below use it for the design of the pavement. So basically we use, say for example, if you are familiar, I'm assuming you are familiar with the term CBR, California Bearing Ratio. So all the design guidelines, including IRC 37, the latest one, the input is for the subgrade is CBR. Obviously, we have to convert the CBR into modulus, and those things I'll discuss a bit later. But the main input will be the strength characteristics of a subgrade. Okay, whether it is in terms of CBR or whether it is in terms of resilient modulus. Okay. So the pavement consists of obviously different layers prepared using different materials. So depending on the relative rigidity, we call it as a flexible or rigid. Say for example, although the term flexible and rigid is like sometimes misleading. Okay, both whether we call, obviously the term flexible is whenever something we can flex, okay, or which we can it can deflect, we call it as a flexible. Okay, the pavement as well the same. Okay, flexible pavement means it flexes. It doesn't mean that rigid pavement doesn't flex, but you have to understand the terminology. So the flexible pavement is more of a bituminous pavement, or as I was saying here, granular pavement. Say if you are not sealing the pavement, so if you are not putting any bituminous layer as well, still we call it as a flexible pavement. Okay. General terminology for the rigid pavement is if you are having a concrete surface. So obviously, if you are familiar with the terminology, these are different layers. So maybe this one surface. Maybe this is the base, granular base, take granular surface. Obviously, you can have upper, lower, and different layers. Okay, so this can be asphalt. Okay, so if this is asphalt, then we call it as a flexible pavement. If the pavement surface itself is an asphalt, we call it as a flexible pavement. Okay, you can have a cement treated base. Okay, if you have a cement treated base, still we call it as a although the terminology, some people call it as a composite pavement, but still we call it as a flexible pavement. Whereas instead of asphalt, if I have a concrete slabs, okay, or concrete slabs or continuously reinforced concrete, okay, in general concrete material, cement, then we call it as a rigid pavement. So the scope of these presentations will be focusing on mostly on the flexible pavement, which is primarily on the asphalt pavements. Okay, as I said, This is
Sir,
subgrade. Yes.
hello, sir.
Yes,
Sir, I have one doubt, sir.
Mhm.
That we are saying that the concrete pavement is a rigid pavement. Is there any other pavement we can call it as rigid pavement, or only one type is available? We are practicing.
No, see, there are different types of concrete pavement. Say, for example, jointed normal concrete
Yes, sir.
pavement.
Sir, my point is that when except the concrete, is there any other pavement we can call it as a rigid pavement?
No, we typically have a concrete or asphalt or unbound pavements, isn't it? So we usually called concrete pavements as a rigid pavements. Okay. So
Okay.
the point I want to highlight here is rigid doesn't mean that it is not flexible. Okay. So for example, concrete pavement and bituminous pavement, flexible pavement can have same deflection. If you are constructing very strong pavements, say for example, if you are having cement treated base, upon that you are putting say very high stiff asphalt, still the deflections might be very low, but we still call it as a flexible pavement. So that is the point I want to highlight. Rigid, so concrete pavements we typically called it as a rigid pavement. Okay. So and we have a bituminous bound and granular. Say for example, there is some pavements, particularly low volume roads, we do not put any asphalt layer on the top of a compacted unbound material. Still we call it as a flexible pavement. Okay. So as I was saying, pavements having a combination of flexible and rigid layers, okay, is called as a composite pavement. So composite pavement can be, say for example, you have an concrete pavement upon which you overlaid with an asphalt. We call it as a composite pavement. Okay. In some countries, pavement with cement treated bases, they call it as a composite pavement. But for this lecture, we assume this the pavement with cement treated bases, we still call it as a flexible pavement. And another important distinguish between flexible and rigid pavement is the load distribution. As I was said in my first slide, or the rather second slide, I said that one of the important function of a pavement is to limit the amount of stress that is coming from the vehicular loads onto that goes onto the subgrade. Say for example, I have a assume this is a subgrade. Okay, assume this is a subgrade. So you can see this is the load distribution. So you have this as a vehicular load. Say for example, this is a wheel load. Okay, maybe I can so assume I have a wheel here. Okay, so load is upon this pavement. So we have different layers. So this one is, I'm saying bituminous mix. Okay, maybe these are other layers. Assume all other. Oh, sorry, I think I should have said. So this is subgrade. Assume, maybe it doesn't matter, but you can assume this as a subgrade. So you want to limit amount of the stress upon the subgrade as less as possible. So otherwise there will be, if there are more stresses, there will be more deformation in the subgrade and there will be structural failure of the pavement. So we want to limit amount of the stress on the top of the subgrade. Okay. So for that we are putting number of pavement layers. Say for example, this is the surface, this is base, bituminous base, and say these are all other layers. So as you can see, this one is E1. Assume elastic modulus of surface is E1, modulus of elastic modulus E3. So usually in most of the cases, particularly in the conventional bituminous pavement, E1 is, it is not always true, but in general. So you can see the load distribution, this is more. So the slope is more for this one and less is for this one. What this means is the stiffer the material, the distribution will be more. So from here to here, it is the distribution is more, and and from here to here the distribution is slightly less. So eventually what we are trying to say is, okay, we are providing the sufficient thickness so that the load distribution or the stresses on the subgrade is less. Whereas in the rigid pavement, the primary difference for the rigid pavement, the distribution, most of the load is distributed by the concrete itself. Okay, the load distribution will be more. Okay, from here to here, although it is the thickness is less compared to this pavement. Okay, so most of the, as you can see, the most of the distribution is done by the concrete pavement. Whereas here, if you can see, this is the thickness of this is more, thickness of this layer is less, but the elastic modulus, say if I'm calling this as E1 dash, E1 dash is usually much more than E1. Okay, so elastic modulus of concrete is usually more than asphalt. That's why the load distribution will be more. So this is another primary distinction between flexible and rigid pavement. The load distribution is primarily the function of concrete in the concrete pavement. What that means is the role of base and granular base, granular subbase is much more important in terms of load distribution in flexible pavement compared to the rigid pavement. Okay. The role of foundation is also. So this, as I was saying, this whatever I have shown in this presentation, in this slide, is whatever I have discussed. Okay. Rigid pavement, as I said, term is misnomer. Okay. As I was saying to you, the concrete pavement, rigid pavement itself deflects, and hence the pavement is not truly rigid. Okay. Some of the pavements, such as interlocking block concrete pavement, say block pavement, maybe I might have one slide later. So this is a block pavement. So although these paver blocks, we call it as a paver blocks. You might have seen these type of pavements, particularly on the footpaths. Okay, although these are made of concrete, they deflect much more than flexible pavements. Okay, so whenever we are talking about flexible and rigid, we have to keep this in mind. Rigid doesn't mean that they do not deflect. Okay, and other pavement type I have picture next to the block pavement is self-filled concrete pavement. It also deflect significantly more than flexible pavement. Okay, so the important point you have to remember is the current convention is to distinguish between whether it is a concrete pavement or non-concrete pavements, like a bituminous pavements, okay, unbound pavement with just a granular material as a surface material. So to distinguish these two, we call it as a rigid and flexible pavement. So obviously you can have a large number of combinations. Okay, two combinations we discussed so far, like a concrete pavement, and flexible pavement. But within the flexible pavement, you can have different combinations. Say, for example, you can have obviously bituminous material here, and you can have a granular base, or instead of granular base, you can have along with granular base, you can also have cement treated base, cement treated sub base, and cement treated sub base. Okay, I'll discuss these terms later as well. Okay, but I hope some of you are familiar. Someone was asking something? No. Okay. So we have a subgrade as well. Maybe you can have a stabilized subgrade. Say some people can choose to stabilize the subgrade with cement. Okay, I can write. Okay, so you can choose whatever we want. Obviously, there are certain guidelines which I'll be discussing in the next class. But you can have different combinations. You can have bituminous material and granular base and conventional subgrade. You can have bituminous surface course, cement treated base and cement treated subbase, and stabilizer subgrade. Okay, maybe conventional subgrade with cement treated base and bituminous. Okay, there are various combinations you can choose from. So payments are subjected to obviously different traffic loads and different climatic conditions. So whenever we are designing a payment, we have to make sure that we are considering the prevailing traffic conditions and prevailing climatic conditions as well. So as I was saying, we can use different types of payments as well, type of material like a bituminous material, cement treated base, cement treated subbase, subgrade. Okay, and also maybe I can talk about geotextiles as well. So there will be a lot of combinations you can choose from. Okay, well, whatever the combination might be, we are designing the payment to perform. Okay, perform satisfactorily. So what is that satisfactory performance that we will discuss in coming slides. So obviously there are different types of payments. So in the next coming slides, what I will be discussing is different types of payments. What is the concept of performance? As I here said, perform. So perform is like a performance. So we expect some performance from the payment. What is performance? Okay, what is perform? How do we quantify the performance? What is satisfactory performance? Okay, how we consider different loading conditions and climatic conditions in payment design. What is the influence of these conditions, these aspects on the payment design? I'll be discussing in next few slides. Okay, so this is, you can see, gravel road or unbound. Sometimes we call it as unbound payments, unsealed payments. Okay, although this photo is not correct one, but there are payments which are not paid. Okay, whatever you are seeing here is a bituminous payment. Okay, on which maybe below this payment we might have a granular base, bituminous layer. Beneath the granular layer, maybe on subgrade. Okay, maybe we might be construction on an embankment as well, as I was talking, an embankment. And most of the payments, concrete payments in India are jointed concrete payments. Okay, so we, as you might be, I don't know whether you can see these joints. Okay, we have a slabs. Okay, around 3.5 by 3.5 meter slabs, or 4 meter by 4 meter slabs we usually have. And in this photo, we are seeing roller compacted concrete. There are, although very limited, there are payments called continuously reinforced concrete payment. Okay, so they usually have a reinforcement in the payment. At some locations in India, we have continuously reinforced concrete payments as well. And recently, we started to have a paneled concrete payment as well. Like these are the slabs, as I was saying, in the conventional jointed concrete payment. We have a 3.5 by 3.5 or 4 by 4 meter panels, whereas in panel concrete payment we have 1 by 1 or 1.5 by 1.5 meter panels. Okay. So there are some advantages of panel concrete payment and disadvantages. Similarly, CRCP has some advantages and disadvantages, but we are not going into those details. And this is a block payment. Again, it is concrete blocks made up of pavers. Sorry, concrete paver blocks made up of concrete. And this technology, which Professor B.V. Pandey, if you are familiar with, he introduced in India this type of payments. Okay, this. So that is different payments. As I was saying, I'll be discussing design process. What is the performance definition of performance? What are different design approaches? What are different design factors, and what is typical design framework? Okay, so design framework for I'll be discussing on mechanistic empirical pavement design. Okay, so if you are familiar, very familiar or slightly familiar with any pavement design, you might be confusing with MEPDG, mechanistic empirical pavement design guide, which is US pavement aid. The pavement. So however, we have IRC 37. Okay, IRC 37, probably most of you might know what it is, but the benefit of people who are not knowing, okay, IRC 37 is a design guideline, okay, for the design of flexible payments in India. So whoever is designing a flexible payment, particularly for national highways and state highways, they have to use whatever IRC 37 for designing a payment. Okay, so the IRC 37 equivalent in USA is MEPDG. So, but do not confuse with mechanistic empirical payment design approach. This is an approach. Okay, whatever the approach that we have in IRC 37 is mechanistic empirical approach. So I'll be primarily focusing on that aspect. So what is a design in general? So for any facility, the design is usually selection of what type of material you want to use. Say for example, if we are considering the building, maybe which type of concrete. Similarly for the pavement as well, what type of materials, which materials you want to use. Okay, and the dimensions of the, actually in other facilities we usually try to determine the dimensions, whereas in pavement the dimension is usually, because our linear dimension is fixed, the thickness we are interested in thickness. So to what thickness? So basically you want to find out, you will decide which type of payment. Usually this has not usually in the hands of designer. Okay, but if you have to design from the beginning, obviously you have to decide on which type of payment. But for example, within the payment, whether you want to go for payment with cement treated base or cement treated sub base. Okay, and number of layers, how many layers you want to design the payment for, and what type of material, whether you want to choose bituminous concrete. Okay, so maybe this you might be familiar, some of you, but for the benefit of others, usually say for example surface coarse material, so you have a bituminous concrete as a surface. Okay, BC is bituminous concrete, and SMA stone matrix asphalt. Okay, so gap graded rubberized mix. Okay. These are different types of asphalt mixes. Okay, although the scope of this presentation is not to doesn't include the water, these maybe you will be coming across these aspects in the later lectures, but I'm just giving you. Okay, for example, we are talking about a base, bituminous base. The typical option we have according to IRC 37 is DBM, dense bituminous macadam. And for the base, we have a CTB, cement treated base. Okay, and or granular base, cement treated sub base, granular sub base. Okay, and obviously if you want to include any geotextile like so there's some comment has come, but I'll come to that comment a bit later. I haven't seen that comment, but I'll discuss. Okay, for example, you want to use geogrid. Okay, so how we can consider the geogrid in pavement design? So all these comes into the design. Okay, say for example, if you are having cement treated base, the design will be different. Design approach will be different. If you are having the geogrid within the granular base or granular sub base, the pavement approach will be slightly different. Okay, so if you are having conventional granular sub base and granular base, pavement approach will be different. Okay, so that's why we have to decide that. We have to decide number of layers, obviously, and what type of material you want to use. And the most important thing, to what thickness of each layer. So these are all, we call it as a design variables. Okay. So essentially, the design is the process of selecting appropriate values for the design parameters. So which are these, in such a way that the facility performs satisfactorily or acceptable manner. Okay. So that acceptable manner is related to the performance. Okay. So what exactly is the performance? I'm going to discuss in next coming slides. Now let me see what is the comment that has come. So does it mean that I have to stop presenting to see the comments? Oh no, I think I can see. Sorry. So can we decide the type of payment, whether to go for a flex? So okay, this question is almost impossible to answer. Okay. So whether you want to go for a flexible payment or rigid payment. So as I said, it is very, I think that is the $1 million question. Okay. So most of the times it is actually in theory, I'm talking about theory, but not practice, definitely. Maybe some of you might answer better than me with that question. But in theory, what we should be looking for the life cycle cost. Okay, as I said, this is only theory. In practice, many other factors influence. Okay, but the life cycle cost means like what is the upfront cost? Obviously, upfront cost is more for concrete payment and less for bituminous payment. And also, for example, maintenance. Maybe maintenance is less for concrete payment and more for bituminous payment, flexible payment. And also, one other important aspect people many times ignore is recyclability. So, okay, concrete payment may last for 40 years, bituminous payment may last for less years. But obviously, concrete payments are difficult to recycle, whereas flexible payments are relatively easy to recycle. So basically it comes to life cycle cost, but obviously the decisions at higher levels, all those dictates the in practice. Okay, so maybe some others can if anyone want to answer that question on behalf of me, you can answer, but my answer is it is very difficult to answer, but in theory it should be based on life cycle cost. So as I was saying, all facilities has to be designed to perform. Okay, should perform over a, what is performance? So they should perform over a design life. So for example, I'm just giving you an example. Okay, my performance criteria, I can say I do not want a pavement to be having rough depth of more than 20 mm. Okay, this is actually this is actually the performance criteria within IRC 37 and similarly many other payment designs as well. Okay, so this is the performance. I'm just giving you an example. So I do not want a payment within its design life. Say for example, I'm designing for 20 years. Okay, so I do not want the depth within the pavement to be more than 20 mm within design life of 20 years or 20% of cracking. I do not want a pavement to be cracked more than 20% within its design life. Okay, that is what the satisfactory performance means. How do we define the pavement performance? As I said, like for example, retting, we define 20 mm is the satisfactory performance. If the depth is less than 20 mm, we may call it as a satisfactory performance. Obviously, this is for the highways we are considering. Maybe for different facilities, these criteria might be different. Say, for example, if we are considering runways. Maybe 20% cracking might not be their criteria. They want much more less cracking within its design life. Okay, maybe for example low volume roads. Okay, where village roads maybe 40 up to 40 red depth is acceptable. So this is not a defined parameter. It can change with the type of facility. Okay. And obviously how we quantify, how we measure, that also we'll discuss depending on what type of performance we are looking at, whether we are looking into rating as our performance criteria, whether we are talking about cracking as a performance criteria, or there are other aspects as well, which we'll be discussing in next couple of slides. So there are primarily two different types of performance: functional performance and structural performance. Okay. So the functional performance is basically a pavement has some functions. Okay. Primarily, so it should be safe to travel, comfort, and economical. Okay, it should be safe to travel. Say for example, safety. Say for you are having a very polished pavement surface. Okay, your skid resistance will be very less, but it is not safe to travel. Or else maybe if you have like a lot of potholes on the pavement, it is not safe to travel, particularly for two-wheelers. Okay, it should safe to travel, and the journey upon the pavement should be comfortable and it should be economical. So these three would come into place. So this is dictated by functional. Basically, this is functional performance is in terms of user. As a user, what the user is looking for. He wants a safe payment surface. And also what he wants is a comfortable ride on a pavement. And what he wants is an economical journey. Say, for example, fuel consumption per unit kilometer, he wants to be as less as possible. So if we are looking into user perspective, that is what the functional performance, which satisfies the functional requirements of the pavement. And as a designer, we are more interested in a structural performance. Okay, structural performance is you do not want pavements to be cracked, okay, or deformed. Okay, so we do not want these. Performance, but as a user, we are interested in a functional performance. But how do we measure, how do we quantify the functional performance and structural performance? I'll be talking in next couple of slides. Okay. So as I said, functional performance is safety. Okay, adequate skid resistance throughout the service life, and which is dictated by polishing and sometimes on the bleeding. Okay, bitumen is bleeding onto the top of a pavement, then also surface of the pavement becomes slippery. Okay, and it is unsafe to travel. And also hydroplaning. Hydroplaning is if you have traveled in a car just behind a heavy truck in a rainy season, when it is pouring, when it is raining, then you would know what is hydroplaning. Okay, so if you're traveling immediately behind a heavy truck when it is raining in a car or a two-wheeler, like we literally cannot see anything. The reason is the whatever water, we call it as a splash and spray. That splash and spray of water will be more because of the hydroplaning. And also hydroplaning is basically exact term is so if you have a pavement and if you have a tire and assume this is a tire, there will be thin layer of water on the top of a pavement. Okay, what that will do is that will bring down the friction between pavement and the tire. Okay, that is exactly actually hydroplaning, but one of the consequences of hydroplaning is splash and spray, which is also not safe. Okay, and but direct consequence is reduced friction between the So you want to address this during the design as well. Okay, obviously we will not consider as a part of structural design, but as a pavement design guidelines, every pavement design guidelines has to address the skid resistance issues as well. Okay, and coming to the comfort, obviously safety is related to the skid resistance, and within the functional performance, as I said, the second one is comfort. So comfort, we usually have a parameters which we call it as a roughness, okay, which is influenced by roughness. So rougher pavement surfaces are less comfortable. Obviously, I do not have to explain that. So roughness is a measure of variation of the surface profile. Okay, say obviously if there are if your surface profile is something like this, okay, we are looking into bigger. This is not a small projections, but the wavelength of each is much more. Okay, so someone has said to me the voice is not audible. Is it not audible? Can you confirm?
It's audible. It's audible.
Okay.
It's audible, yeah.
Okay. So whoever has message, just check your audio settings. Okay. Roughness is basically variation in the surface profile. So if there are more variations in the surface profile, the pavement we call it as it is more rough. Okay, how we measure obviously this is a function of some of the structural distresses as well, such as rutting and uneven deformation, etc. Okay, structural failures such as crack, all these influence the roughness. So there are various parameters or various indices which we quantify the roughness. Say PSI, which is present serviceability index, is a function of cracking, patching, rutting. So this is basically one of the so if ASTO 1993 pavement design is one of the first pavement design which is developed based on the actual field data. Okay, so this has been quite popular until recently. Okay, so in this one, the parameter they have optimized is they have correlated with used for the pavement design is PSI. Okay. They used this as a performance criteria. Okay, which present service PSI. Okay, uneven index is one of the indices we use for the quantifying the roughness. Merlin roughness, international roughness index. Okay, so just for your benefit, I'll not spend a lot of time on what is fifth bill integrator Merlin and international roughness index. Maybe these might be discussed later in lectures, not by me, might be others. But if you have any questions, you can ask me towards the end, but I'll quickly go through all these. As I was saying, this is PSA, permanent present serviceability index, which is a function of slope variance, rut depth, crack, and patched area. Okay, you can see these are CP, rut depth. So PSI you can calculate from these expressions. Okay, this is the performance criteria that people have used in ASTO 1993. Okay, ASTO is American Association for State Highway Transportation Officials. Okay, so it is US pavement design. Okay, still many states in US use 1993 guides and they use PSI as the performance criteria. Okay, and as I was saying, this is a fifth wheel bump integrator. Okay, so we call it as a response type roughness measurement equipment. in which what you have is this is the wheel, okay, which is you have a car or some vehicle which tows this fifth wheel. So what it does is it measures. Say you have here a wire. Whenever there is a bump, so whenever there is a bump, what it will do is it will trigger. So it will count number of triggers, this fifth wheel bump integrators. Obviously, if it is a bigger bump, the trigger number of triggers will be more, okay, because it is so you have this spring, okay, spring attached to the chassis of this fifth wheel, and depending on the unevenness, so we have a measurement, roughness measurement, okay. So this is what the fifth wheel bump integrator is. So basically a vehicle tows, so vehicle goes in this direction, it tows this fifth wheel, and then however if there is more bumps, okay, more unevenness, the bump integrator value will be more. If it is a smoother pavement, bump integrator value will be less. Okay. There is another equipment called Merlin equipment. Okay, this is machine for evaluating roughness using low cost. They call what we call machine for evaluating roughness using low cost instrument. So they have this uneven surface, and this is a tire, okay. It just look like a cycle tire. It is just a cycle tire, whatever the cycle tire, and you have here a probe. Depending on, obviously you have more the roughness, the readings, we collect some readings here. So if it is smooth, the readings will be, the deviations of the reading will be less. If it is roughness is more, the deviations within the whatever the readings that we are collecting from here is less. So reading, what we do is for every meter we take the we put this probe on the ground and we take a reading here, okay. So if you want to know more details of Merlin or bump integrator, we can discuss towards the end, okay. And the most used index for roughness is basically International Roughness Index. Basically this work was carried out in maybe 10-15 years ago, maybe even older. What people have done is because there were multiple equipment people used to use, like some people use 50 wheel integrator, some other people use different equipment. So to harmonize everything, the people have studied a big study. Basically it was like a study involving number of countries, particularly developing countries. What they have done is under the, I think, World Bank study. Okay, what they have done is they harmonized all the equipments and they come up with a single parameter called a IRA, International Roughness Index. Okay, what it is this is an hypothetical. Okay, hypothetical car which represent car body mass and axle mass, and these springs and dashboard represents the what we say vehicle suspension system, and these springs represents the tires. Again, this is an hypothetical, we call it as a quarter car, and we collect the pavement profile and we run that profile using these parameters in a computer, so that we get a index called International Roughness Index. Okay, so from that study the output is IRI as a function of Merlin value. Okay, IRI as a function of bump integrator value we have got. Say for example, whatever values we get from the bump integrator or Merlin, or there are other equipments, if if we put those values in an equation that is proposed, we would get IRI. So the objective is, in some countries what they say is they want to maintain IRI to be less than certain of these values. So this is about functional performance. Coming to the structural performance. So this is retting. Obviously, you might be knowing what is retting. So within the wheel path, usually we have a retting. Okay, it could be because of with deformation in bituminous layer. And also maybe deformation in subgrade as well. Okay, so this is structural performance. So one of the criteria we usually have is, okay, retting should be less than 20 mm as I was saying. Okay, such criteria. In some designs, we have a retting as a criteria. As I said, retting can be in bituminous layers or subgrade. Say for example, here it is more likely in the subgrade. You can see this layer has deformed, this layer has deformed, and this layer has deformed. So it is potentially issue with the subgrade, the deformation. And if, for example, if you have only deformation, something like this, okay, if you do not have any deformation in the layers beneath, then the issue is with the asphaltness. So as a designer, you may want to address the retting issue as well, structural performance. Okay, and other aspect we talk about the structural performance is cracking. Okay, there are two types of cracking, bottom up cracking and top down cracking. Okay, so conventionally we design against the bottom up cracking. So we say bottom up cracking is nothing but, say, because of the repeated applications of the load, what happens is this layer on the top of the pavement bends. Okay, say for example you have a pavement, because of the load application it will slightly bend. So because of the bending, what will happen, there will be more tensile strains at the bottom of this asphalt layer, and after repeated application of the load, which we call it as a fatigue, a crack starts at the bottom of a pavement. Okay, and it once it starts, it propagates to the top. We call it as a bottom up cracking. Okay, in some pavements, basically because of various other reasons, particularly durability issues. Okay, basically what happens is bitumen that is present in asphalt layer, it ages and it becomes brittle. Once the bitumen become brittle, what happens is a crack initiates at the top and it approaches to the bottom in this direction. We call it as a top down cracking. Conventionally, what we do is we design against the bottom up cracking. Okay, and we make sure that top down cracking doesn't occur in terms of mixed design. Okay, but in an actual design, we should take care of both bottom up and top down cracking as well. Okay, similarly, the retting in bituminous layer and retting in subgrade. But how do we know whether the crack is subgrade, top-down cracking or bottom cracking? What typically we do is we take a core. As you can see, these are the cracks. What we do is we take a core, cylindrical core, and we see whether the crack, if there is a crack that starts from here and say it stops somewhere here, then it is top-down, bottom-up cracking. Obviously, you will, in that case, you might not get where you want to get. But if it propagates up to here, we conventionally think that it is a bottom up cracking, but if you can see this crack has propagated, say, something up to here. Okay, so we can see this as a top down cracking. Okay, you can see here as well the where we are taking from. So it has propagated to some depth. So crack has initiated at the top of the pavement. So different agencies adopt different approaches for design of a pavement. Okay, these are all whatever I discussed in last 10-15 minutes is what is exactly the performance. We discussed about functional performance and we discussed about structural performance. Okay, but whether we should design for structural performance or functional performance. So whether we should consider say functional performance IRI as a design criteria or retting or cracking as a design criteria. As I said, it depends on the agency, which agency we are looking for. Say for example, IRC 37, which is the design guidelines for flexible pavement design in India. We consider the retting on the top of the subgrade and bottom of cracking. Okay, but as I was saying earlier, ASTO pavement design, it considered IRA as a criteria, but most designs consider retting in the subgrade and bottom of cracking as the design criteria. Okay, the assumption is basically if we, sorry, I think I should structure. So the assumption is if we take care of structural performance, in most cases functional performance satisfies. Okay, if we make sure that there is no retting, there is no cracking, then the functional requirement is usually met. Based on that criteria, we design. Okay, so so as I said, depending on the agency, different agencies adopt different criteria, and also different agencies adopt different approaches. Okay, so far I introduced two design methods. Okay, one is ASTO 1993 design method, and the other I was talking about IRC 37. Okay, so I think in one of my slides I was saying IRC 37 is basically mechanistic empirical design. Okay, so this one is empirical design. These are two different design approaches. There are mechanistic as well, mechanistic design approach as well, which is conventionally the third one, but there is no design available just on mechanistic, but that's why we just focus on empirical and mechanistic empirical. Okay, so that is what. So whether it is an empirical design approach or mechanistic empirical design approach, we always need performance data of the pavements. Okay, so the performance data is nothing but say what we do is we collect data. Okay, for say I collected data for 10 years. Okay, what is the amount of cracking? Okay, so I measure, go to the site. Either I go to the site, there are now presently there are advanced technologies, we call it as network survey vehicles, etc., etc. They can collect the data for you, and you collect all the distress data, cracking, retting, or whatever distresses you are saying, or IRI. Okay, because we talked about cracking, retting, and IRI, I'm just focusing on these three parameters. Okay, so what we do is we collect it for a number of years and see how the payments, obviously IRI will increase, cracking will increase, retting will increase. Okay, so we collect that information. So that data we call it as a performance data. So how pavement is performing, how cracks are increasing with time on a pavement, how roughness is increasing with time on a pavement. Okay, how retting is increasing with time on a pavement. So that information we collect that information, we call it as a performance data, the observed performance, and then correlated to one or more design parameters. So I'm just giving you an example. Okay, say you might be knowing what is the CBR. Okay, California bearing ratio. So what I do is in theory, again, this is not what people have done, but if you want to develop a performance criteria, what we do is we say I construct a payment with the different CBR materials. Okay, say one having say 2% CBR, one having 5% CBR, one having 10% CBR, and I construct a payment and I monitor that payment and collect this information, the retting, cracking, and IRA information for number of years. Okay, year 1, what is the cracking? Year 2, what is the amount of cracking? By year 3, what is the amount of cracking? That information I collect for number of years, and I correlate that with the design parameter I'm interested in, CBR. Okay, So if the CBR is 2%, say for example, after 10 years, I have say 30% of cracking. Okay. Maybe I'll draw here. Okay. Say for example, 2% CBR, 3%, 5% of CBR, and 10% of CBR. Maybe I'm talking about 5-10 years. Okay. So what I'll do is I'll collect the information here, and here. Every 5 years I'm collecting the data. So based on this, what I'll do is, okay, if 5% of CBR, okay, say for example, I got 20% of cracking here, if it is 2%, and 20% of cracking here. So what I'll do is, okay, if my CBR is 2%, the design life will be 5%, 5 years. If my criteria is 20% of cracking is my performance criteria. Similarly, if it is 10% CBR, the design life will be 10 years. So this kind of information we'll collect usually for us. We should be able to develop which we call it as a performance criteria. Okay. So performance criteria is exactly what is this one, and I explained you very simple one. Okay, but it is much more complex than that one. So, and we relate here, the performance parameter we have taken is CBR. Okay, CBR versus performance. Okay, maybe you can see the graphs here. This is IRC 37 1984 version. Okay, so earlier people used to have CBR versus performance equation. You can see here the thickness of the construction, how thick you want, and here you have for different traffic levels, and you have different CBR versus. People might have collected the information as such information and developed such plots. Okay, that is that type of design approach, or the developing a performance criteria. We call it as an empirical pavement design, and the criteria we develop, we call it as a empirical criteria. Okay, so we take some empirical parameters such as CBR in this case, okay, and we correlate with the performance, that we call it as empirical criteria, and the design which uses empirical criteria, we call it as empirical pavement design approach. Okay, say there is another approach which we call it as a mechanistic empirical criteria. Okay, in which, in this case, we correlate, we use say here we used CBR, but instead of CBR we use a mechanistic parameter. Like mechanistic parameters are nothing but stress, strain, and deflections. Okay, we have an equations for the stress. Instead of CBR, we'll have a stress, strain, stress or strain or deflection versus performance, as which is what we use in IRC 37. Say for example, I just giving you an example. So number of cycles to failure usually have K1, 1 by strain per K2. Okay, so NF is number of cycles to failure. Okay, and this is strain at the bottom of the asphalt layer. So what we do is we collect the data, performance data, and we identify what is K1 value and what is K2 value. From these we do basically regression analysis. Okay, and identify, we develop a model. This we call it as a mechanistic empirical performance criteria. Okay, so what we do is, say we discuss a CBR versus performance criteria. In this case, similar to that one, what we do is we construct different pavements, okay, with initial, say initial tensile strain values, different tensile strain values, and we collect the performance data, and we have a failure criteria, say 20 mm, 20% of cracking. Okay, our typical example, 20% of cracking. What we do is we find out after how many load cycles the pavement is coming with 20% cracking, and we correlate these two. Okay, this we call it as mechanistic empirical criteria. So we are calling it as a mechanistic because we are correlating with the mechanistic parameters such as stress, strain, and deflection. We are calling it as empirical because we are using regression analysis to find out K1, K2, because the data collection again is an empirical data collection, isn't it? And also approach, we call it as a mechanistic empirical pavement design approach. Hope this is clear, but if it is not, just let me know. So next couple of slides is whatever we have discussed so far. Okay, performance of pavement is correlated to, in empirical criteria is performance of pavement is correlated to, yes.
Sir, could you please mechanistic criteria, sir, again?
So empirical criteria, in empirical criteria, we use empirical parameters such as CBR with the performance. Okay. So mechanistic parameter, which is basically, if you have seen IRC 37, if you have ever used IRC 37, we have two equations. Okay. One is NF, number of cycles to failure, as a function of tensile strain at the bottom of the pavement, obviously elastic modulus as well. There is another parameter, this is for fatigue, and there is another one which is rutting. Okay, number of cycles to failure as a function of compressive strain at the top of the subgrade. So empirical parameter, mechanistic models or mechanistic empirical models are the functions. Instead of empirical parameter, we have a mechanistic parameter. So if we have a NF, number of cycles to failure, which is number of load repetitions, maybe I can say, for now you can think this as a number of years to failure. Okay, although it is not exactly correct, but you can think it as a number of years to failure. Okay, if I have CBR, which is not a mechanistic parameter, which is a empirical parameter, if my number of years to failure is a function of some empirical parameter such as CBR, then it is a empirical model. Okay, and if my model, the damage model, or the what we say criteria, performance criteria, is having a, in terms of stress, strain, or deflection, and we are correlating that with a performance, whether in this case fatigue or rating, then it is called a mechanistic parameter. Okay, so in both cases, in either cases, what we do is we collect the information. Okay, maybe, although I might be taking a bit longer, but let me explain. So what I do is I construct different payments. Okay, say as the same example, like a 2% CBR payment, say 5% CBR subgrade, and 10% CBR subgrade. Okay, and what I do is, say for example, just giving an example. So I collect every 2 years to say 4, 6, 8, and 10. Okay, just an example I'm just giving. And I collect data. So I'm talking about cracking data. Okay, it can be cracking, or it can be retting, or it can be IRI. Okay, but I'm just this is years. Okay, this is 2%, 5%, and 10%. Okay, say for me, my cracking progression after 2 years, it has come to say 3, say 6, say 9 and 12 and say 15. Okay, when I have a payment on the top of 5% subgrade, 5% CBR subgrade. Okay, I have say 2, 4, 6, 8, 10. Okay, 10 percentage. Okay, this is cracking percentage. Whatever I'm having here is cracking area or cracked area. You can see. So this one, 1, 2, 3, 4, 5%. Say what I would say is I do not want my performance criteria. I do not want my cracking to be should be less than 5%. Okay, then what I have, so if I have a payment on 10% CBR, okay, I have within 10 years I get 5% cracking. Say whereas if I have a payment on a 5% CBR, I have around 5 years. Okay, so CBR 2, 5, 10. Okay, and fail. Payment when it is failed, my failure criteria is if a payment has greater than 5% of cracked area, I consider that as a fail. Okay, so this one for 5, this one is failing in 5 years. Okay, if it is a CBR, this one is failing in say so 10, it is a 10 years, isn't it? 10%, 10, it is failing in 10 years, 5%, 5 years, and 2% CBR, when it is failing, around say 3 years. Okay, so this is what? So this is NF or NY, number of years to failure. For now, you assume it is years, but years and traffic is the same, isn't it? You have as a function of CBR. This is what an empirical parameter, empirical equation is. This is what our earlier versions of IRC worked on. So as a function of CBR and the whatever chart I have shown you earlier. So this chart, if you see, as a which is a function of CBR versus number of cycles to failure. Okay, so number of cycles to failure is this one. So different design traffics. If it is 10 to 15 MSA or whatever it is. Okay, there is for different traffic categories for different CBR, you have different curves. So that is empirical parameter. Whereas in the mechanistic parameter, the mechanistic empirical design criteria. So what exactly it is? So instead of CBR, rather you have a mechanistic parameter. Okay, so tensile, as I said, why we cracking in IRC 37, we consider bottom up cracking, isn't it? Bottom up cracking we consider. Okay. So we said bottom up cracking occurs because of high tensile, say if it is a bituminous layer, there will be high tensile strains at here which propagate to the top. What we do is we run the analysis within the pavement and for a particular pavement thickness, and obviously we'll have different tensile strength. Obviously, if we are constructing on 2% CBR, your tensile strain will be more. So, and if we are constructing on 5%, it is slightly less. If you are constructing on 10% CBR, your tensile strength will be even lesser. Say, for example, this is epsilon T1, epsilon T2, and it is epsilon T3. So epsilon T1 is greater than epsilon T2 is greater than epsilon T3. So based on this information, we have an epsilon and we have number of years to failure. Okay, same information. This information we call it as a performance data. Okay, using the same information, what we do is we develop an equation as a number of cycles to period, or ES for this matter, as a function of tensile strain. Okay, this we call it as mechanistic empirical criteria. So this criteria is a basis
Sir,
for the yes.
sir, in both the empirical and mechanistic data collection, we are measuring the percentage of cracking, right, sir?
Percentage of cracking is one criteria, but you say, for example, in IRC 37 we also have rating. Okay, for example, if you're developing
Okay, sir, okay, sir. We are seeing percentage of cracking only. For percentage of cracking, what we are measuring, sir, for data
cracked,
collection?
so cracked area, say for example, if you have a pavement, okay, it has some cracks, something like this. Okay, what is the percentage of area? Say for example, if you are talking about one say 100 square meters, in 100 square meters area, how much percentage of area is cracked?
Okay, sir. So we are
So
not measuring the tensile. So what is the tensile strain, sir? How can we get the data related to tensile strain?
tensile strain data you get, say for example, you have constructed the pavement, isn't it?
Yes, sir.
You constructed the pavement, you know the thicknesses when you are constructing a pavement.
Yes, sir.
Okay, and what you do is we have different softwares. Have you heard about IIT Pave?
Yes, sir. Yes, sir.
Okay, you put that pavement composition in IIT Pave, or there are many analytical softwares. Okay, using linear elastic theory, basically what we determine is we'll determine the tensile strain. Okay, for that tensile strain, as a function of this one, you will collect the data. When you are constructing the pavement, you will know, isn't it? So you are constructing, say 10 pavements. For each pavement, you will know the tensile strain, and you will collect the performance data, and you correlate both of them.
Okay, sir. Yes, sir. I
Okay.
understand.
So I have
Thank
taken a lot of time on this one, so I will spend less time explaining the next ones, which are basically whatever I discussed in next few slides. Maybe after going through next 3-4 slides, we can break for a few minutes and rejoin again. Okay, just I'll read these ones. If any explanation is needed, I will explain. But whatever I discussed so far is summarized here. Okay, experience of performance, which is experience performance, means whatever the performance data we collected correlated to the pavement design parameters. Okay, typically subgrade strength, thickness, etc. by statistical means, which is we are talking about empirical criteria. Okay, the relationship does not explain the fundamental mechanistic behavior of different materials used in the pavement. Okay, so this is the shortcoming. Okay, these 3 points are the shortcomings of empirical. So why we have to design mechanistically? Why we have to? Why can't we use empirical approach? Is this one? Say because of mechanistic, because we have only CBR value. Okay, or some other parameter, but we are interested in mechanistic parameters, means like you can use whatever the material you want, and also empirical methods cannot extrapolate. I should have space here, with confidence beyond the range of experience. Whatever the data we have taken, within that limit we have to work on. Okay, with analytical methods or mechanistic empirical methods, you can extrapolate beyond. Okay, may not work for new material, new climatic condition, new traffic conditions. Okay, this is one of the shortcoming for empirical one. Coming to the mechanistic empirical performance criteria, it explains the different phenomena, as I said, stress, strain, and deflection. Okay, our IRC 37 takes strain and also stress as well. If we have a cement treated base, we consider stress as well. So stresses, strains, and deflection occurring in the pavement with reference to physical causes. Okay, for example, loads, material properties, and etc. etc. So we will see these in the tomorrow's class. What are these models? How these are correlated to the performance? We'll see these things, but I'm just giving you the background. The relationship between the phenomena and the physical causes is explained using the mathematical models. Say, for example, we in the previous example, we correlated with the tensile strain with the number of cycles. So tensile strain at the bottom of the base will cause the bottom up cracking. So we are correlating that with the failure, isn't it, performance data. So the mechanistic approach is integrated with empirical approach in the selecting limiting value of stresses, strains, and deflections that causes the failure of the pavement. So this is what the phenomena or the philosophy of IRC 37, which is the major objective of this my 3 days lecture. So this is the most important sentence. So mechanistic approach is integrated with empirical approach in selecting the limiting value of the stresses, strains, and deflection that causes failure of pavement. So basically we select the limiting tensile strain. Okay. What is that? I'll discuss when we discuss actual pavement design. Okay. But this will be more clear. The relationship between phenomena, stress, deflection, and failure explained by empirically obtained relationship, which estimate the number of load repetitions to failure. So our objective of a pavement design is to find out number of cycles to failure, isn't it? So this is a design life. We call it as a design life. Okay. Failure, as I said, in IRC 37, failure is 20% of cracking or 20% of rutting. 20% of bottom up cracking in bound layer, 20% of rutting in subgrade. Obviously there is a CTB as well, but I'm talking about conventional. So to reach this one, either whether you reach this one first or this one first, that is what we call it as a design life. Okay, say for example 20% of cracking is reaching in say 15 years. Okay, or maybe I'll talk in terms of now, from now onwards, in terms of years rather than million standard axes. 20 million standard axle for a particular pavement section, and say 20% of rutting I'm reaching in 30 MSA. So my design life will be smaller of these two. So my design life will be 20 MSA. So we set NFA as a function of tensile strain. So in generally pavement design, your NF is fixed, isn't it? Say for example, you are designing a pavement for 20 MSA traffic. This you fixed, which is you fix this one. What you want to find out is tensile strain. What is the tensile strain? When I analyze in a analytical software, I should get tensile strain, limiting tensile strain less than a particular value. So what we'll do is we'll input NF in this one and find out tensile strain. And what we do is we run the analysis in a software for different pavement thicknesses and find out at what value of thickness this tensile strain is less than this limiting value. So that is the philosophy of the pavement design. If it is not clear, it will be more clear when we discuss later. Yes.
Sir, can I break 10 minutes, 10 to 15 minutes?
Yes. Anyway, we are going to stop. Let me explain this slide. After that, we can break for 10 minutes. Okay.
Okay, sir. Okay, fine.
Okay. So I'm talking about performance criteria, isn't it? So these two, this is in US. In USA, these are the tests: Vasho road test, Asho road test, and SHRP. So this is a part of Asho road test. They have, what they did is they have constructed the pavements, different pavements. Okay, flexible pavement. You can see this is a test loop. Different pavements of different thicknesses. Okay, whatever I explained to you earlier, like a CBR versus performance data, same exercise as a part of Asho road test. They have constructed different pavements and they have collected data and developed the performance criteria. Whatever performance criteria, similar performance criteria we discussed, the similar thing they have developed as a part of Asho road test. Similarly, in India as well, there are 3 research claims: R6, R58, R81. people have collected the data and the performance criteria NF as a function of tensile strength has been developed. Okay, these three schemes. Okay, we can break for 10 minutes. In my computer, it is 10:40. Maybe we can meet at 10:39. We can meet at 10:50. Is that okay?
Okay, sir. Okay, sir.
Okay.
All the participants please take a 10 minutes break and let's continue. Okay, sir. Thank you.
No problem.
Thank you, sir.
No problem.
Thank you, sir.
questions, just ask me, because this is the most important point that I discussed in last maybe 15 minutes, 20 minutes, that we will be using in next tomorrow's class and class after. So I will discuss again for just for 5 minutes. Okay, this is basically heart of entire payment design. Okay. Again, I'll be repeating this towards the end as well, but just so payment design in like any other design, for example, any structure, what we do, we take some what we say seed values for the dimensions of a structure. Similarly, we take is seed thicknesses. Say we start with certain thicknesses, okay, and we run the analysis. Maybe if you are designing a structure, maybe if you are analyzing in some FEM tool like STAT Pro or ANSYS or Abacus. Okay, what the output of that one is stress, strain, and deflection. Similarly, what we do is, say for example, I take a trial thicknesses 100 mm of bituminous layer, maybe 250 of unbound layer, and you have a subgrade here. Okay, and so we have thicknesses and we have material properties. Here you have an elastic modulus, E value, and Poisson's ratio, modulus, and Poisson's ratio, mu. And what you do is you model this in a linear elastic model. Say for example, in our case, we model this in IIT PAVE, which is linear elastic model. So, and what we get is, we get, as I noted here, tensile strain at the bottom of the bituminous layer. I'm just giving you an example. Okay, you will have similarly, it is the same as compressive strain at the bottom of the subgrade as well, but we'll come to that later. Just to explain you the concept I'm getting. And this tensile strain, say for example, you are designing a pavement for 20 MSA. What is MSA? Million standard axis. Okay, how we can convert our traffic data into million standard axis, I'll discuss later, but assume that 20 MSA is 20 million standard axis is our target. So you want to design a structure, pavement structure, with which can take 20 million standard axial loads. Okay, so now we have a function which is number of cycles to failure as a function of tensile strain. Okay, you have run the pavement and you got a tensile strain value of some value, and then you input that into this one and you get some NF, and you check whether this NF is greater than or greater than this 20 MSA. If it is not greater than 20 MSA, then what you do is you increase the thickness. Say for example, you increase this to 120 mm. Okay, and run again analysis. If you increase the thickness, your tensile strain will be less, isn't it? So your tensile, if this tensile strain is less, your what happens is, if you remember, I have given in general expression for 1 by strain power K2. Okay, if this tensile strain is less, your NF will be more. Now if you have increased the thickness, your tensile epsilon T will be less. That will increase your NF, and then you check whether this 20 MSA is less than this NF or not. Okay, if it is less than, that is your design thickness. That is how is general design philosophy is. But essentially what we have to understand is how do we convert the traffic load into 20 MSA, which is part of my next lecture. Okay, but this is what a pavement design is about. Okay, this is a mechanistic empirical pavement design method. As I said, it can handle various load types and new materials as well. Different materials can be used, and the reliability concept is also used. We typically call this method as an analytical method. So as I was saying, this is the traffic factors. Okay, so this is bituminous layer. We are interested in the tensile strain at the bottom of here. When a load is applied here, you get a tensile strain. What you have to remember is unbound materials. This is bound, isn't it? Bound asphalt layer. This one is unbound. Okay, so unbound material, they do not fail in tension, isn't it? They cannot take any tension. Only bound materials take in the tension. That's why we take the tensile strain at the bottom of a bitumen bound layer. Okay, so what are the things we have to consider is like the tensile strain here, and obviously as a part of pavement design, this they undergo different climatic conditions. For example, there will be the the temperature of this at this location will be much more than temperature somewhere here. I mean, depending on the temperatures, and also what type of material you have. An asphalt material, you have unbound material, and you have subgrade. We have to consider all these. Okay. So coming to the traffic loading. So here I'll only discuss very briefly. Okay, as I said, I have more detailed lecture on traffic loading. Okay, on after following this one, but here I'll primarily focus on other design factors. Okay, so obviously traffic loading, you have a different axle loads. Okay, say you have a tandem axle, tridem axle, and a number of different axes. You have to consider that into design. Okay, you have number of repetitions. It is not one single load. You have a large number of repetitions as well. You have to convert that into pavement, consider this into the pavement design. And you have pavements with different contact area and different vehicular speed. Okay, so how we take account of axle loads, how we take account of number, you have different types of axle loads, and each axle load type you have different number of repetition. It is not single repetition, and each repetitions are different, and depending on the type of vehicle and type of tire used, the contact areas may be different, and contact areas or contact stresses might be different. As you can see, this is what the tire imprint, whatever you are seeing here is a tire imprint that is collected on the how. So the shape of the tire imprint you can see, and all these has to be accounted into a pavement design. Okay, these three, how we take account into the pavement design. These three, what we do is we. So is my screen gone? I think someone started sharing. So is my screen still coming up for you?
Sir, PowerPoint was missing. Yeah, now it's okay.
No, what you are seeing, can you tell me? Hello? Hello, can you tell me what you are seeing at the moment?
The design factor screen.
Sorry?
Design factors. Slide of
Design
design
factors. Okay, good. Thank you. So we'll discuss these three, like whatever the axle load, different types of how we convert this into median standard axles. We'll discuss in next lecture, but maybe next 5-10 minutes I'll discuss what is the importance of vehicle speed, how the vehicle speed influence the pavement design. Okay, so as you can see, people what they have noted is different vehicle speeds. What you are seeing is a compressive stress. Okay, they have measured the compressive stress. at a particular, obviously the same vehicle, the load and time, the amount of time that they what we say, the time spent by each vehicle at a point. Say, for example, I have a pavement. Okay, a load is somewhere here. A vehicle load
Excuse
is.
me, sir. The sound is very low, sir.
Is it very low?
Yes, sir.
For everyone, it is the same.
You are clear.
Sir, it is fine.
Okay. So if you have a point somewhere here within the pavement, and if the vehicle comes here, what is the amount of time spent by the vehicle, or what you can say this, what is the amount of time this point, this particular location is loaded by vehicle of different speeds. As you can see, the slower the vehicle, more the loading time spent on a particular point. So what exactly this means? This means because bitumen, you might be heard that asphalt material or bituminous mix is a viscoelastic material. So which is a time dependent material. That means longer the time period, its modulus will be less. In essence, the what we say, the loading time will influence the how material behaves. So the longer the loading time, lesser the modulus of the material. So what I'm trying to say here is, whenever you are selecting a material properties for the design, we have to consider this aspect of a asphalt material as well. So viscoelastic aspect that we have to consider. And also you can see different stresses will be there. Actually, this is when a load is passed, this is the front axle. Okay, this is rear axle. You can see what is the how much stress difference is there from the front axle to rear axle. Okay, so these aspects we have to consider when we are designing the. Okay. And you can see here people have the same previous research. As the speed of the vehicle is increasing, the duration of the pulse also changing. Okay, pulse duration is also changing for 40 mm, 190 mm, and at different depths. So at different depths, the with the decrease in the speed, the pulse duration is increasing, or with the increase in the speed, the pulse duration is decreasing. So pulse duration decreasing means the elastic modulus of asphalt layer is increasing. So maybe why it is doing that? Obviously, if you, one of my first slides, I said the load distribution will be something like this. Maybe if we assume say some 45 degrees at different, if you think about different points at different depths, the load duration will be, the load distribution will be more. So the load duration of the vehicle for this point is this one, L is this one. So obviously time equal to length by velocity, isn't it? So the point here has more length, and whereas point say this is A, this is B. Okay, A is having more length and B is having less length. So if length is less, the time that is loaded is less. If length is more, the time loaded is more. So this is just an example I'm showing. Maybe if we want to calculate this, maybe we can calculate, do these calculations tomorrow if we time permits. But I hope this gives the sense of importance of vehicle speed. In essence, what I'm trying to say is, depending, the faster the vehicle is, less the loading time, and the less the loading time, the modulus of the material of an asphalt is more. So in general, what you have to remember is the loading time influence the material behavior as well, particularly asphalt material. Unbound material, the influence is less, but asphalt material, it influence is more. Okay. So this is, and also I was talking about loading time. Obviously, the intensity of the stress also changes. If this is a load at this depth, the intensity will be more. At deeper, the intensity is less. Even the more deeper, the intensity is even lesser. But you can see load duration is increasing. So if it is shallower, the load duration is less. If it is deeper, load duration is more. So we have to consider all these aspects in general if you are designing a pavement. But how we consider these in IRC 37, that we'll discuss in later. And also coming to the climatic factors, there are different climatic factors. For example, temperature, moisture condition. Okay, how these influence. these aspects also need to be considered when we are designing a pavement. For example, elastic modulus of asphalt material at higher temperatures, the modulus will be less. At lower temperatures, the modulus will be more. How we are considering that in a pavement design, that will be discussing, but essentially what I'm trying to say is that has to be considered. Okay, maximum service temperature. Say for example, most of the retting happens during the summer midterm. Okay, so that has to be considered either when you are designing a pavement, whether it is a structural design or mixed design. Okay, some we try to address as a part of structural design, some we try to address as a part of mixed design, but our discussion will be more on a structural design. Okay, minimum service temperature, temperature gradient within the layer, and moisture. For example, if the moisture content is more, for example, if you are considering a pavement immediately after monsoon, the unbound material and soil will be completely saturated. If it is a completely saturated in condition, the modulus, elastic modulus of unbound materials, which is soil and the granular base, granular subbase material, elastic modulus of those layers will be less. Okay, so these aspects we have to keep in mind when we are designing a pavement. Okay, so other point we have to remember is the temperature have less influence. Temperature and vehicular speed have less influence on other unbound soils and aggregates. Okay, but the temperature and also vehicular, as a similar to vehicular speed, it has significant amount on bituminous binders and thus on the mixes as well. So that's why when we are selecting a material property, we have to test the material considering these aspects: the importance of loading time and the importance of the temperature. That is less influence both loading time. Loading time is basically changes with the vehicular speed. Okay. Similarly, temperature, loading time and temperature, we have to choose according to the design guidelines. Okay, we have to test at particular loading time and particular temperature as specified by the design guidelines. Okay. So these things we have already discussed actually. So we said bitumen is a thermoplastic or an viscoelastic. The properties of bituminous mixes most affected by change in temperature, as we discussed. Different process sites will have different service temperatures. So we have to consider either in a structural design or a mixed design these aspects. Okay, temperature has to brought into the design aspect. Okay, low temperatures usually causes the different type of defect. That is also low service temperature. You have an transverse cracking, which we call it as a low temperature cracking. That is also we have to consider when we are designing a pavement. And most of the fatigue cracking usually occurs during intermediate service temperature. Okay, for a major portion of the service life, the pavement is exposed to intermediate service temperature. That is say around 15 to 35 degrees, say, I should say. Obviously, this is not an exact boundaries. It depends on location to location. So most of the times pavement temperature will be in this temperature, and in which fatigue cracking is more critical. Okay, at high temperatures, we more or look into retting. Okay. I think this is the repetition of the previous slide. And at this point as well, we discussed materials. Okay, the elastic modulus and Poisson ratio of subgrade and each component layers is required. Okay, when I showed you when you are analyzing a pavement, you have to have an elastic modulus of a pavement. Okay, and also Poisson ratio at what we call it as a material input factors. Okay, material inputs for a pavement design. Similarly, as I was saying, bituminous mix is mostly influenced by repeated loads and also load, which is load duration and also temperature. So when we are measuring these properties, you have to consider these as well. And there is another aspect called whether we want to consider it as a linear elastic or non-linear elastic. That is again different subject. But usually we assume during the pavement analysis, we consider the materials as a linear elastic, but we indirectly assume the non-linearity of these materials. How we consider those aspects, we'll discuss it in the tomorrow's class. Okay, so this is what I was discussing earlier, and also I try to summarize whatever discussed so far in this design framework. So for a pavement design, actually pavement design is a trial and error approach. Okay, so again I'm going to my previous example. Say for example, you are tasked to design a pavement with 20 MSA traffic. Okay, and what you do is you do first trial. Okay, first trial I take as a pavement composition. Okay, say I'm designing only 3 layers. I have just an example. I have a bituminous layer and granular layer. Okay. Just an example I'm just giving, which is having some modulus E1 and Poisson ratio mu1, and this one having E2 mu2 and subgrade having E3 mu3. Okay, and say I start with 100 mm, say 200 mm, and this is infinite space. Okay, and I model this thing, okay, in a structural response model. So we have many tools, okay, which say for example IIT Pave is one such tools which does this one for us. Okay, we input this into structural model, and whatever we get from this structural response is strains, stresses, and deflections. Okay, so say for example we got a tensile strain of certain value. Okay, we have obviously we have that model I was discussing about, NF equal to K1 epsilon T power K2. Okay, what you get epsilon T and you input into this, we call it as a distress prediction model. Okay, we input into this model and we get number of cycles to failure for this pavement, whatever pavement we are considering here. Okay, so say for example I got 15 MSA. Okay, so this pavement can last for 15 million standard axis with whatever the failure criteria we were this model has been developed for. Say this model is developed for 20% of cracking. Okay, so what it means is if I have a pavement with 100 mm bituminous layer with E1 mu1 and 200 mm of granular base with E2 mu2 and subgrade with E3, okay, it will last for 15 million standard axis. Okay, with a cracking after 15 million standard axis, I get a 20% cracking. Okay, that is assumption. Whether we get that different things, that is assumption. So, but we need a pavement with 20 MSA traffic. Then what we do is this is not sufficient. So then what we do is we increase the thickness of either bituminous layer or granular layer. Okay, you do trial and error. So instead of 100, what I'll do is I'll increase it to 120 mm. Okay, so that is distress model. Then this is performance requirement. This performance requirement is, this is what the comparison. Okay, so whether my NF is greater than 20 MSA or not. Okay, so if it is yes, you finalize the design. If it is no, obviously you will change the material, either change the material properties, okay, or change the thickness. Okay, maybe you may choose a stronger bituminous layer or increase the thickness. Say now if I increase the thickness to 120 mm. Okay, now again I do repeat this one. I again model that into an analytical software and I get the stress and strain values and I input that into this one and I check whether I get NF and then I check whether NF is greater than 20 MSA or not. If it is yes, yes, I finalize the design. So that is what the design is. Okay. I hope you understood how we design, but obviously we will we'll take some examples as well when on the third day and also if possible tomorrow as well. But my next presentation is about finding out how we from a traffic given a traffic spectrum how we can determine 20 MSA, whether it is a 20 MSA or not, how we'll determine convert a traffic spectrum into million standard axis. That I'll be discussing in next maybe 45 minutes or so. So I can take a couple of questions if you have any. So if you understood whatever we are discussing, if you are comfortable with whatever we are discussing today, it is very easy to follow to whatever we are discussing tomorrow and day after tomorrow. Okay, can I take this as you do not have any questions? Okay. So what I'll be discussing now in this lecture is, say we have different vehicles. We have different cars, trucks, buses, cycles. Okay, trucks also different types of trucks you have. Okay, each have different axles. Okay, how we convert into a in previous examples, say I was saying in MSA, how do you know the pavement you are going to design will have 20 MSA? Say if you are designing for 10 years, okay, how do you know? So that calculations will not calculations but calculation procedure, how we convert this into million standard axis, and what are other approaches other than considered. We call this approach as equivalent single wheel load approach. Okay, so what is equivalent single wheel load approach? What is MSA is million standard axis. Okay, maybe I should have mentioned this one earlier, but hoping that assuming that you know what is MSA, this is million standard axis. Okay, what is standard axis? Okay, how we convert all the axes into standard axis. Okay, that we'll be discussing in next in this presentation. So obviously we have different types of vehicles, all these vehicles, but we do not consider all the vehicles for pavement design. Okay, maybe for the geometric design and the other aspects, we'll consider these two-wheelers, passengers, cars, and etc. But we only consider what we call it as a commercial vehicles. Okay, only vehicles that are having laden weight of more than 3 ton we consider for the design of the pavement. Okay, there are two reasons for why we consider only the commercial vehicles. They rather two concepts. One we call it as a I'll tell. So the damaging effect of each vehicle. Okay. So cycles the damaging effect of cycles, two-wheeler and cars is much later. We'll talk about fourth power law. Okay. These are insignificant. That's why we do not consider what we call these traffics that are traffic which carrying the vehicles that are less than 3 tons. Whatever the number might be, we do not consider because because of the fourth power law. What is fourth power law? I'll discuss a bit later. We will not consider this one. We only consider the traffics that are commercial vehicles that carry more than 3 tons of laden weight. You have different types of commercial vehicles. Okay, you can see according to IRC 3, these are type 2, type 3. This is a tractor unit with front axle, rear axle. Okay, front axle, single axle. We call this as if there are 2 axles immediately this one, we call it as a tandem axle. Okay, you have here 3 single axles. Okay, here you have 1 single axle, 2 single axles, 1 tandem axle. Okay, you have here for the tractor units itself having a tandem axle. Okay, so different configurations, you have different loads. Obviously, you will, if you are designing a pavement, whatever the pavement you are going to design, this will have the combination of all these different what we say traffic loading. Okay, how we convert, what considerations we have to make. You can see this is a tridem axle, so 3 axes. This is tridem. Okay, if you notice here, this is usually the rear axis are dual wheels. Okay, and front axis are single wheel. Usually front axis are single wheels and the rear axis are dual wheels. Okay, here also you can see tridem axle. This is single axle dual wheel. This is tridem axle dual wheel. This is single axle single wheel. Okay, buses also rear axle, usually you have a dual wheel single axle. Okay, some buses might have tandem axle as well, but essentially what I'm trying to say is usually rear axles are dual wheel. Okay, so here this one as well, tridem axle dual wheel. This one single axle single wheel. This tandem axles. I'm repeating this one so that you are familiar with the what is tridem, what is tandem. Okay, so according to Morse circular, okay, relatively recent, we also have a legal limits. Okay, legal limits for example, single axle 2 wheel, you cannot have more than 7 ton. Single axle 4 wheels, okay, you cannot have, maybe I might have say for example, the legal axle limit for single axle 2 wheel load is 7 ton. You cannot have more than 7 ton. Single axle 4 wheel. So on either side of the axle, you have a dual wheel assembly. Okay, you have 11.5 ton axle. So this is tandem axle, which means like you have 2 axles, but with the 2 wheels on. So in total, you have 8 wheels. So 21 tons. So these are all limits that are proposed by Morse, but in reality, in any pavement, if you do the axle load survey, you usually find many vehicles that are beyond this legal axle limit. Okay. So the loading is transferred to the pavement through pneumatic tires. Obviously, all the tires are pneumatic tires over contact areas which are not circular and at a contact stress which is not uniform. So the important point I'm saying is usually we are saying here it is not circular and non-uniform contact stresses. Usually we have, I think I have shown you earlier one of the imprint. Okay, this is imprint collected. You can see obviously this is not circular, isn't it? And the stresses are also not uniform. But in design, we consider it as a uniformly distributed stresses and circular contact area for simplicity. Okay, so maybe I'll come to this point why we assume this as a uniform contact stress. I'll come a bit later, but you remember when we are analyzing a pavement, we assume a uniform contact stress and usually circular loading area. That assumption is reasonable, particularly non-uniform. Why it is reasonable, we'll discuss in later slide. Beside that, we also, beside the vertical stress, obviously because of the loading, whatever the stresses we were discussing, we have a vertical stress. We also have horizontal forces that are applied at the surface. Okay. Vertical is straightforward, but when during braking or during like what we say, turning of the vehicles at the curves, usually you have some horizontal force also applied at the surface of the pavement. Okay, you have different duration of load application. Okay, this we discussed earlier as well. Depending on the speed of the vehicle, each pavement element is subjected to different load durations and different rest periods. Obviously, rest period is, say for example, this is your pavement, a wheel load passes. Okay, and say for example, if this is a front axle, and immediately after within less than a second, within milliseconds time, you will get another load which is rear axle. But maybe after 1 second or 2 seconds or after 1 hour or 2 hours, you may get second vehicles. So you will have different rest periods. That is what the rest period is. Okay, so first rear axle causes one load pulse and the front axle causes a different load bus, and vehicle after this vehicle causes different load bus. That we call it as a rest period. That rest period we have different. Why we are talking about rest period? This rest period is as well is very important because, as I was saying, asphalt material is a thermoplastic, which means that temperature and time dependent. Okay, after when a load is applied, it deforms. When the load is removed, it recovers. But unlike elastic material, what is elastic material? Okay, elastic material, when you say for example, if an elastic material is loaded and unloaded, the whatever the deformation is, it is recovered instantaneously, whereas viscoelastic, it will not recover instantaneously, it will take some time. Okay, that's why the load rest period also has a significance in a material properties when we are discussing about the behavior of different pavement materials. I discussed about what what I wanted to talk about tire print. I have shown this one. Okay, coming to regarding the pneumatic tires. Okay, maybe I'll use different color. So pneumatic tires, we have to consider 3 parameters. Okay, obviously pneumatic tires are, you know what is pneumatic tire. So which is inflated with air, which has inflation pressure. Usually 700 kilopascal inflation pressure, okay, typically. So 3 parameters need to be considered. What is total weight? What is the shape of the contact area? How the pressure is distributed over the contact area. Okay, as I said, the shape is not circular, but in analysis we consider this as a circular. The distribution of pressure is not uniform, but we consider it as a uniform. So coming to the why we get non-uniform contact pressure, there are 2 reasons. One is obviously, as you can see, it is not completely occupied. You can see these gaps. Okay, even within this boundaries, the pressure is not uniform. You can see the marks. Okay, at some locations it is the mark is more, at some locations it is less. The reason is, say for example, your tire pressure is low inflation pressure. Okay, then what happens is lot of load is taken by the walls of the tire. Okay, obviously tire is reinforced. You have reinforcement within the tire. Okay, so more pressure will be at the walls of this tire and less will be inside. So you will have a less wall tires are in compression and contact pressure is greater than the tire pressure. Okay, that is when the low inflation pressure. If you put more tire, more pressure, so walls of the tires are in tension. Okay, if the inflation pressure is more, what happens is there will be less stress here and there will be more stress here and the distribution will be different. Say for example, maybe I will somewhere here. Okay, say for example you have low inflation pressure. The pressure stress distribution will be, so you have more stress here and like this. Okay, so if it is high inflation, this is tire, obviously tire boundaries. Okay, so if the inflation pressure is more, usually what happens is you have less pressure. It'd be exaggerating, but just to explain you the concept, it is the difference won't be this much, but the stress distribution will be something like this. So it is non-uniform usually. So for us to have a uniform stress distribution and reasonable distribution, you want this, we call it as a rigidity factors to be 1. So if you maintain an inflation pressure of 0.7 megapascal, usually rigidity factor around 1 and the contact pressure will be uniform. Okay, so how do we calculate the contact pressure? We know wheel load and you have an area of imprint, and you from that you can calculate the contact pressure. Yes, hello, someone was asking something. I cannot hear, but if others hear, I can. Maybe if your audio is not very good, you can leave a message in chat. If not now, I'll look at it later. Okay, during at the end of presentation or in between the presentation. But I cannot hear at the moment whoever is asking. So this I mentioned already. We have a vertical stresses. We have unidirectional surface shear stresses, and we have centripetal shear stresses. This centripetal shear stress is nothing but, as I was saying, if your tire pressure is usually low, what happens is, you can see there will be more pressure here on the edges of the tire, and it will cause shear stress at the edges of a tire. Okay, say for example, if you are assuming the circular contact area, okay, as I was saying, your stress distribution will be something like this. Although I'm slightly exaggerating, but so there will be more stresses here, which become as a shear stresses as well. Okay, because the tire, obviously, if it is less inflated, if you might have seen there will be bulge to the tire. Okay, it is trying to push in this direction, and pavement is trying to come back. That's why you have a centripetal shear stresses as well. Typically, we'll ignore this one, centripetal shear stresses, and also unidirectional shear stresses. We only consider the vertical stress. Okay. so that is what I'm saying. Normally only uniformly distributed vertical surface stress equal to tire pressure is considered for the analysis. Okay, so why uniformly distributed? So basically the shear stresses, whatever the ununiform distribution, is only at the surface of the pavement. Say if you have pavement thickness, okay, maybe you might have ununiform stresses, but as we go deeper the pavement, the stress distribution is usually uniform. By the time it reaches, say, if you run the analysis in an FEM, finite element method, or any linear elastic analysis, usually you find non-uniform stress distribution only at the typically at the top, say 2 mm or 5 mm or 10 mm. Beyond that one, you usually have a uniform stress distribution. That's why we consider uniform stress distribution for the analysis, pavement analysis. And also, as I was saying, we usually consider the shape of the contact area as circular, although the shape can be depend on the inflation pressure, tire age, and pavement surface. Okay, we usually consider circular tire imprint, but different people consider different shapes. For example, circular in IRC 137 we consider circular shape, but some people consider rectangular shape, okay, as something like this, rectangular shape contact area. Some people consider the area similar to this one, okay, and we consider the circular contact area. Okay, so how much the contact area we can obviously calculate from the area of the imprint, circular area imprint. From that you can calculate, and the V load, contact pressure. From that you can calculate the area. Okay. So these points as well we discussed when we are discussing the principles. Okay, traffic loads applied over several years, up to we consider up to design life period. The traffic volume normally increases with each year, isn't it? Like obviously depending on the location, the growth rate changes. Vehicles on a given road carry different loads. Vehicles on different facilities carry different loads. Obviously, for example, port payments, different type of traffic. Highway payment, different type of payment. If it is a runway, different type of traffic. So all this has to be considered. The wheel loads are applied over design different portion of the payment, not at a single location. So we call it as a lateral vendor. Okay, say for example, if this is a payment plan, okay, one vehicle might go here, another might go vehicle might go here. Okay, so the location of the flying of the traffic is not at a single location, not like a train. For train, it is always at a single location. Whereas for the roads, it is at different location. For runways, even if we call it as a lateral wander. Okay, lateral wander. So, for example, if we draw a frequency distribution of, say, at the center of the assume this is a single lane dual, I mean a two-way direction, or a single lane. So usually that distribution will be something like that. You have at the central line you have more traffic, and as we go the traffic is distributed. Okay, this is frequency. Okay. And usually for highway payment, standard deviation of this normal distribution is usually be around 200 mm, okay, or 150 to 200. Whereas for the runway, it is usually say 2 meters or 3 meters, up to 3 meters. Okay, because you do not have a channelized traffic. Whereas if we are looking into port pavement, usually they take a single path. The lateral wander, the standard deviation for this distribution is around 50 mm. Okay. So how we consider this, because all vehicles do not follow the same path. More vehicles may follow this path, lesser vehicles follow this path, and even some vehicles, very limited, they go at the edge of the pavement. Okay, how we consider this lateral wander in pavement design, that we'll discuss the coming slides. Okay. The first one is traffic forecast. As I was saying earlier, the traffic growth, there will be a traffic growth with each year. How we consider the traffic forecast, that it will also help in design if the traffic volume during different periods of a design life can be estimated. These estimates can be done from the traffic volume prevailed by base year and by selecting appropriate growth factors and projected techniques. Obviously, say if you are considering this is a time, okay, annual average daily traffic, for example, with the time it will increase, isn't it? It will not remain constant. At what growth rate it is increasing up to design life. So if it is a design year, projected design year. Say for example, this is 0 is present year, and this is end of construction, and this is end of design life. Obviously there will be growth of traffic each year. What is this growth factor is based, and also what is the cumulative traffic, which is like area of this curve, cumulative traffic, that we have to determine. So a typical approach followed by ARC is obviously number of n equal to 365, number of days. A is initial design traffic, as I was saying. This is traffic, average daily traffic, for example. Okay, if this is 0, by the end of the construction of a pavement, there will be some traffic, isn't it? That is this point. Okay, A is that point, multiplied by 1 plus R. R is growth factor, at what rate the traffic is increasing. So N is number of what we say, years. Okay. So using this factor, so design period, N is design period, R is the growth rate of commercial vehicles expressed as a fraction. Okay. So whether it is 2% or 4% or 5%. Okay. IRC 37 has some assumption. If in the absence of R, what is the default value we can take, that we'll discuss in tomorrow. Okay. Usually 6 to 7%, 5 to 7%, I should say. And if you are having present traffic, obviously what will be the traffic by the end of construction, you will not have that information. So if you have to predict the traffic after end of the construction, you can use this expression. P is the number of commercial vehicles per day as per the least count, R. Okay. Using R, you can express. X is, what is X? From present year to the end of the construction period. What is that is X. So you can use this expression to determine your A in here. Okay. So I hope this is clear how we project the future traffic. So A is the number of commercial vehicles per day by the end of construction of a pavement. R is growth factor, usually between 5 to 7%. Okay, I mean, we traffic model from the, you get this R value from the traffic models. Okay. And N is design life, and you will not have A, because by the when what we say, when by the time we finish the construction, at that what is the projection that we calculate using this expression. Okay. So that is about traffic forecast. What we are interested is the cumulative traffic for design period N will be adjusted for after calculating N, we have to adjust for directional distribution. Okay. And lateral placement of the characteristics of the wheel on the pavement and load spectrum. So actually, although we are calculating this way, this is, we will not be using N value. We are not interested in what we call total number of commercial vehicles. We are interested in total number of standard axes. That is what we are interested in. So first what we do is we correct N for the directional distribution of the traffic. Directional distribution is nothing but say for example you have 2 lanes. Okay, I'm just giving you 2 lanes. Not all the traffic pass in one lane, isn't it? It is some distribution, some traffic will go into, maybe I can draw this as a median, and I have 2 lanes for this as well. Okay, so from the traffic calculations, what I'm calculating is whatever the total traffic that goes into this lane in one direction. Okay, but I have 2 lanes. This is lane 1, this is lane 2. Not all the traffic goes into the lane 1, not all the in lane 2. So how do I consider that I have to adjust for this distribution of the traffic in different lanes and the distribution of the traffic in different direction if you have only single carriageway. Okay, that is what the directional distribution of the traffic. We have a factor for that one, and I talked about lateral wander as well, which is lateral placement of the wheel on a pavement. As I was saying, in a single lane, most of the vehicles will follow single path, but some vehicles deviate from the other path. How we consider that into as well, we consider, and the load spectrum. Obviously, different vehicles follow different path. I mean, different vehicles have different axes. How we consider that into load conversion, load traffic conversion, we'll discuss that in the coming slides. So all the commercial vehicles, as I was saying, do not take the same lateral position on the highway. Lateral wander we discussed. Depending on the type of facility, whether it is a 2-way or multiple lanes, and also depending on the number of lanes, the path that wheels of the commercial vehicles, all the wheels of all the commercial vehicles utilizing the pavement during stress the same, get different reputations of the load. So how we consider this in the design consideration? So for example, 4-lane divided highway. So the load distribution will be something like this. There will be some overlap. Okay. So maybe some vehicles come into this lane, some vehicles come into this lane, wheel path. So what is the critical portion of the flexible pavement that we? So this is basically critical path, because some vehicles are coming from here to here, some vehicles will be coming from here to here. So this point is stressed more considered to all other points, particularly this portion is stressed more. Okay. How we consider that in pavement distribution, as I was showing. So here you can see the distribution. What this is a wheel load characteristics for a single lane, single carriageway. The distribution can be, you can see from the 3.5 meters from the edge of the carriageway, this in 1 meter from within this one, almost what they are saying, 51% of the traffic is within this 1 meter of the road width. Okay. So IRC having some factors Okay, for example, you are having intermediate, so lane with 5.5 meter road width, you have a 75 percentage of, you have a 0.75 as a factor, 0.75 factor. If you are have a 2-lane single carriageway road, then you have a 0.5 as a factor. So you multiply your n, whatever your n you are getting from the previous expression, you multiply with these load distribution factors. If it is a 4-lane single carriageway, your distribution factor is 40%. Okay, total number of commercial vehicles in both directions. Say for example, if you are having dual carriageway roads, okay, dual 2-lane carriageway roads should be based on 75%. For example, you have a dual carriageway, 2 carriageway, okay, say but 2 lanes, the example which I am discussing. And in that case, what you do is you calculate n for one direction, okay, and multiply that n with 0.75. You only consider 75% of the number of commercial vehicles in each direction. Okay, say if you are having 3 lanes, here I have shown you 2 lanes, but instead of 2 lanes, if you have a 3 lanes dual 3-lane carriageway, your multiplication factor will be 0.6. 60% of the traffic only you consider. Say for example, you have 4 lanes. Okay, your multiplication factor will be 0.45. Okay, you multiply. Essentially, what you do is you multiply this with load distribution factor, LDF. Okay, depending on the whether you have a dual carriageway or single carriageway, and if you have a dual carriageway, how many lanes you are having, you have a load distribution factors as presented here. The IRC 37 guideline has these distribution factors, which I'll show you tomorrow. So load consideration is in design. So we have 3 different approaches. One is fixed traffic approach, one is fixed vehicle approach, and variable traffic approach. So in IRC 37, the approach we are considering is fixed vehicle approach. So that is what standard vehicle, standard axle. Okay. So which is 80 kilonewton axle. So we convert all the traffic into 80 kilonewton axle. We call this as a standard axle, but we have others as well: fixed traffic approach and variable traffic and vehicle. Okay, so in fixed traffic, what we do is we consider the heaviest anticipated vehicle in the main is considered, and we do not consider the number of repetitions. Okay, we design only for the whatever the heaviest anticipated vehicle, we design for that one. Okay, this is rarely used. Pavements are designed for a single wheel load. That single wheel load is heaviest anticipated load, and the multiple wheels converted into equal single wheel load. Okay, this is single traffic approach. We do not have we do not usually consider this one for highway pavement design. So some airport designs, okay, for example, ICAO pavement design approach, the old one, not the new one. They used to use this single traffic fixed traffic approach. So they considered the heaviest aircraft that is flying on the runway, they consider, and they design the pavement for that heaviest aircraft. So what they have is usually some curves like this, say for each aircraft. So number of such aircrafts versus thickness. Okay, so as the number of such aircrafts is increasing, the thickness will increase. So they have such approach, but as I said, not very commonly used. So fixed traffic approaches, you fix the aircraft. Say for example, I have Boeing 777, B777. Usually the stresses of B777 is very high. So what we do is we see how many such aircrafts are coming, and as the number of aircrafts are increasing, your thickness will increase. You do not consider whatever the other traffic and other aircrafts are coming. Okay. So our approach, which is the most important and most widely used approach, is fixed vehicle approach. Okay, although here it is said fixed vehicle, actually in theory what we are considering is fixed axle. Okay, so we consider 80 kilonewton single axle is considered to be standard axle load, which we fix. Okay, design is governed by number of repetitions of standard vehicles or axles. So what we do is we convert, say for example, maybe so I have say I'm just giving an example. So 30 kilonewton axles, 50 kilonewton axles. Maybe I should give a range, isn't it? Maybe so. Some range, okay, maybe 10 to 50. I'm taking an average, 10 to 40. 0 to 40, whatever it is. Okay, I'm taking the average. So 50 kilonewton, some 60 kilonewton. Rather than confusing, let me put okay, so I have say as I said, we consider only the commercial vehicles. So 30 to 50 kilonewton, so 50 to 70, 70 to 90, 90 to 100, and so on you will have. So you will have say per day, you might have say this one is 100, this one is 50, this one is 90, this one is 60, something like, we call it as axle, whatever here we call it as axle load spectrum. Okay, axle load spectrum, this is frequency and this is axle load group. Okay, and as I said 80 kilonewton will be taken as a standard axle. So for example, the intermediate value I'm taking it as 80. So I have 80 kilonewton vehicles per day. So what I want to do is I want to convert all this is 95, this is 60, this is 40. So all this group, this group, this group, and this group should be converted into this 80 kilonewton group, which we call it as a standard axis. Okay, so how we convert this into a single one? So what the assumption is, the in terms of damage, whatever the damage this 80 kilonewton vehicle load is causing on a pavement. Okay, say for example 95 kilonewton will cause more damage, isn't it? Compared to 80 kilonewton. Okay, and also this is 60 kilonewton will cause less damage than the 80 kilonewton. So you will have a multiplying factors. So you convert this one, you have a 40, you have a 60, 80 and 90 kilonewton load groups. Okay, these are load groups. So I was saying you want to convert everything into 80 kilonewton. Obviously 90 kilonewton will cause more damage to the pavement than 80, and 60 will be causing more damage than the 80. So you have to multiply these numbers, this frequency with a factor. So say A1, A2, A3, maybe A2, A3, A4. Oh, sorry. You will not have any factor, isn't it? A1, A2, and you will have, because this is 1. Okay. So what you do is you multiply 100 with A1, you multiply 50 with A2, and you multiply 60 with A3. So if you see, this is A will be equal to 1, and A1 will be less than 1, and A3 will be greater than 1. So this A is called damage factor. Okay. How we will calculate these A values, we will discuss in next few slides. So, so multiplying the repetitions of a given axial load by a equivalent axial load factor. This is equivalent axial load factors gives the equivalent number of 80 kilonewton axial load repetitions. Okay, the factor that I was A value that I was showing earlier, we call it as equivalent axial load factor. Okay, most design follow this approach. Some of the equivalent repetitions obtained for all axial load anticipated during the design period is used as design parameter. Maybe I'll write it a bit more clearly if I have confused you. Maybe although we have started 15 minutes late, but after explaining this one, I'll stop. The rest of the part we can discuss tomorrow. So we have say our example 30 to 50, 50 to 70, 70 to 90, 90 to 110, 110 to 130. I'm just giving you an example. This is a load group, different axial groups, maybe axial groups, and you have frequency, which is a number of vehicles per day. Okay, so I have the average. I'm just taking it as an average. So 40 kilonewton in kilonewton. This is units is kilonewton, and this is number of vehicles per day. So this is 60, this is 80, this is 100, this is how much is this one? 120 kilonewton. Say I'm having this one as 30, 50, 80, 60, 20. Okay. So I want everything to be converted into, this is 80 kilonewton, isn't it? So everything to be converted into this one. So my total standard axis is, I have to multiply this one with a factor. I have multiplied this one with a factor, multiply this one with a factor, A1, A2, this is A3, and A4. Okay. So as I was saying, the 80 kilonewton will cause some damage, say X. Okay. What is that damage? We'll discuss later. Okay. Some damage has caused by 80 kilonewton. So for a 100 kilonewton load group will cause more damage. The damage caused by 100 kilonewton, this is say 80. Okay. So the damage caused by 100 kilonewton or kilonewton group will be more than damage caused by 80 kilonewton. So my A3 factor will be greater than 1. Okay, and A will be 1, A2 will be less. The damage caused by the 60 kilonewton group will be less than 80 kilonewton. So basically you multiply with all these factors and you sum of all these factors, we consider it as a design traffic standard axis. So that is how you convert all these loading groups into. So these factors, we call it as a equivalent single axis factor, wheel load factors. Okay. The sum of all these is standard axis. That is what that text means. So So multiplying the repetitions of a given axial loads, repetitions is whatever the frequency we were discussing. Repetitions is frequency I have shown, number of vehicles per day. Okay, of a given axial load. So we have seen different axial load groups. Gives the equivalent number of 80 kilonewton load repetition. Okay, sum of the equivalent repetitions of each load group will give the all the axial load anticipated during the design period is used as a design parameter. Most design methods follows this approach. Okay. Variable vehicle and traffic, just 5 minutes. Okay. Variable vehicle traffic is nothing but we consider entire load spectrum. Okay. For example, IRC 58. Which is concrete pavement design, usually consider entire load spectrum, which uses the cumulative damage approach. Okay, what is cumulative damage approach? It is not required, but if you are learning IRC 58 design approach, we usually consider entire load spectrum. Okay, we do not convert each load spectrum into equivalent load spectrum. Basically, what we do is we consider whatever the damage caused by this load group, damage caused by this load group, damage caused by this load group, and damage caused by this load group, each individually. Basically, this is x100, x, this is x120, isn't it? X120, x100, x80, x60, x40, and sum of all these should be less than 100%. Okay, that is what cumulative damage approach is. But in flexible pavement design, according to IRC 37, follows equivalent axial load approach, which is fixed wheel approach. Okay, basically we convert equivalent load into a single loads. Okay, this is what we equivalent single wheel loads. And also we have to convert different axial loads into the single equivalent. So I will stop here. Maybe I'll take just 1 minute. We'll finish this one. Obviously, in IRC 37, we are taking 80 kilonewton as a standard axial load, but the different design approaches. For example, if you look into French guidelines, they take 120 kilonewton as a standard axial load. Okay, it doesn't have to be 80, but in IRC, we take 80 kilonewton as a standard axial. So we said equivalent axial load factors are used to convert different axial load into equivalent factors. So equivalent axial load factor defines the damage caused to the pavement by one application of axial load under consideration relative to the damage caused by the single application of a standard axle. This also we discussed. Okay. So equivalent standard axial load is sum of, actually this is sum of Fi to Ni. This we discussed. F is the equivalent axial load factor, that As we have discussed, and N is frequency that we have discussed. Okay. Here we discussed, isn't it? So you get some value here, some value here, some value here, somewhere. Sum of all these values is basically, if this is frequency F1 A1, F2 A2, F is this 30, F1 is this 30, and A1 is that factor 50, F2 A2, F3 multiplied by A3. Obviously here A is 1 because it is 80 kilonewton axial load group, and F3, F4 A4. Sum of all these, sum of Fs from all the load axial groups will give the standard axial loads that is plying on the pavement. Okay. So that is what this expression is. M is number of axial load groups and equivalent axial load factor, number of applications of the ith group during the design pavement. So how we obtain this F value, equivalent axial load factor? That we'll discuss tomorrow, and how we convert. Maybe we can take an example. I have an example as well here. I hope to finish this today, but I couldn't. But it may take 15-20 minutes, which I'll be discussing tomorrow. But if you have any questions so far, I can take those questions.
Sir, please do share the today's presentation.
Yes, yes, I'll share with today's presentation with you. Okay. Any other questions? So to whom I can send this presentation? Can I send it to Mr. Sharma?
Surely, sir.
Hello.
Yes.
Sir, can you repeat or describe the load distribution diagram for 2 or 3 lane roads? Because there is a mixing up of the load distribution diagram. So how we design what are the design aspects for that?
No, say that. Repeat that question, please.
Sir, for the 2-lane or the 3-lane road, can you describe us the load distribution diagram, the trapezoidal diagram which you have shown initially?
Yes, yes. Say, for example, so I mean, others can leave. If you want to listen, you obviously can listen. Say, for example, this is 1 lane and this is 2 lane. Okay, some vehicles go here, some vehicles go here, and this is a typical wheel path. Assume. Okay, whatever maybe I'll use a different lane. So this is a wheel path. Typically, this is the wheel path you can assume. So obviously so most of the vehicles, they're supposed to go on this wheel path, isn't it? They half meter from here and maybe half or 1 meter from the edge of the pavement they go, but the second wheel will go somewhere here. So most of the vehicles will be there. So the distribution will be something like this, with some standard deviation of as I was saying, around 1.5 or something like that. Okay, and some vehicles might be coming going. Not all vehicles in this lane will move in this. There is some vehicles that can go into this lane as well, isn't it? During wandering. Okay, and this some of the vehicles in this lane also have some distribution, something like this. Somewhere like this. So essentially, if I draw this one here, okay, so some vehicles distribution something like this. This is this wheel path. So maybe this is wheel path 1. This is what I'm drawing is this is wheel path 2 for the other lane. Okay, so this distribution will be something like this. Okay, and at this location there will be more traffic, isn't it? This is lateral wander. Are you asking this lateral wander or lane distribution factor? Lane distribution factor is slightly different. Okay,
I'm not asking, sir. I'm not asking about lane distribution. I'm asking about the intersection of 2 wheel load paths. Intersection.
This is the intersection, isn't it? Some vehicles come in this direction, some will be in this direction, but majority of the traffic will be somewhere here. Okay.
So how do we take care of this in the design of the road?
See, in the design of the road is we take in terms of lane distribution factors only. So we are considering the load. So see, this area, whatever this area, which is this area is not heavily stressed. Actually, this area is mostly stressed, isn't it?
Yes.
Okay. So actually what is happening is your traffic is, if you are assuming everything in a single point, your traffic will be something like this, your line. Okay, maybe your traffic will be something like up to here, but it is because only lateral 100 there will be less reduction in the traffic. Okay, so that we are considering, we do not have any special factors, but that factor is incorporated into lane distribution factor only, in which basically if you have a 2-lane dual carriageways 0.75, 3-lane 0.6, 4-lane 0.4 factors. Okay, we are not specially considering this in the design, but in more rigorous designs you should be considering that as well.
Okay, sir. Okay, sir. Thank you.
So any other questions? Okay, so tomorrow what we'll be discussing is, maybe I'll discussing an example. I mean, first I'll obviously discuss how the load distribution factors has come. Okay, the A's, whatever A I was showing in my previous calculations. So for example, here these A's, what are those A values for each load group, how they have come, I'll discuss. And I'll also discuss the an example how we can convert into an axial load spectrum into standard axis. Okay, after that I'll discuss IRC design procedure, and maybe if we can if we still have time, we can start with an example, and the third day we will discuss only examples. Okay, and I'll share this presentation with you today, and also I will share this IIT Pave software as well, either today or tomorrow. I will share with you today, so that I suggest you to install that software. Okay, if we have time tomorrow, we'll do an example, but you will definitely need that day after tomorrow. So you install that software so that I can, it will be helpful when I'm demonstrating, you can parallelly work on that one. Okay.
Also for this spectrum, you will give some Excel file. Hello. This load spectrum, will you share some Excel files, or we need to prepare?
So tomorrow I will, tomorrow the example I'm talking about, I'll have only slide I will show you. But day after tomorrow, when we are working on the example, I will give some synthetic data with Excel axial load spectrum as well. Okay. See, my objective is not to give the Excel sheet, isn't it? My objective is you should be able to produce that Excel sheet.
Okay.
Whatever
okay.
you are learning, so by the time end of this these 3 days, you should be able to produce the Excel sheet by yourself. There is an axial load spectrum, you should know how to produce it.
But you will be sharing the Excel sheet for all the load data, right? Vehicle load data.
Yes,
right?
yes, that I will do. But that will be third day, not tomorrow.
Okay.
Okay, but tomorrow I will give the example in a simple example in a slide. Okay. So hopefully this is clear. I will see you tomorrow, unless you do not have any questions. Thank you.
Thank you, Dr. Kuna. Thank you very much.
Thank you.
Thank you, sir. Thank you so much, sir.
Thank you.
And I will again see you participants tomorrow at 9:45.
Thank you, sir.
Thank you. Mr.
Thank you, sir.
Mr. Kuna, please share the material, whatever you wish to share with the participants.
Yes, I'll send you the PowerPoints, these two, and also I'll share you with the software which they might have to install in their computer.
That's right. IIT Pave.
IIT Pave. I might not use that tomorrow, but day after tomorrow definitely.
Okay. Thank you.
Okay. I'm leaving. Okay.
Okay. Thank you very much.
Thank you, sir. Thank you so much.
Thank you.